Welcome back. We're continuing our deep dive into the OEIS. Today, we're looking at entry day 000147. It's called labeled trees of diameter 5.
Always interesting how just a sequence of numbers can give us so much structural info about math objects, you know?
Yeah.
Like in this case, a very particular type of tree.
Right. And before we get too far into the numbers themselves, I think it's good to make sure we're all thinking about the same thing. Can you remind us what a tree in graph theory actually is?
Absolutely.
Yeah.
So at its core, a tree is a connected graph, but importantly with no cycles.
Okay.
So imagine like a network of points connected by lines, right?
Mm-hmm.
And the key is you can go from any point to any other point, but there's only one path.
Oh, I see, yeah.
Only one unique path to get there.
Okay, so no loops or like roundabout
Yeah,
ways.
exactly. Just a clear branching structure.
Got it. And so for this specific deep dive, we're talking about trees with a diameter of 5.
Right.
What does that diameter actually mean?
So the diameter of a tree is the length of the longest, shortest path between any two nodes.
Okay.
So in a diameter 5 tree, the farthest apart any two nodes can be is 5 edges.
Gotcha.
If you're taking the shortest route, that is.
Makes sense, yeah.
Okay.
So then the OEIS entry mentions labeled trees specifically.
Right.
What's special about those?
In a labeled tree, each node has a unique identifier, like a number. Think of it as each point in our network having a specific address.
Okay,
So it's not just the connections, but their individual identities.
gotcha. Now, the thing that always gets me with these sequences is, well, this one in particular, is that the first 5 terms of A000147 are all zeros.
Oh, that's key. That
Yeah.
tells us that you can't actually have a labeled tree with a diameter of 5 if you have less than 6 nodes.
Yeah, why is that? What's so special about having at least 6 nodes?
The OEIS entry gives us a nice visual. It says any tree of diameter 5 can be visualized as 2 rooted trees, each of height 2 joined at their roots.
Okay.
So picture like 2 small trees, both symmetrical. A central trunk branches 2 levels up. You fuse those trunks together. That's your basic diameter 5 tree.
I see.
Less than 6 nodes, you just can't build that structure. You can't have those 2 trees in the middle.
So those initial zeros are more than placeholders. They're actually telling us something important,
Exactly.
like about the minimum number of nodes to even build this tree.
Exactly, the minimum ingredients.
I love that. Okay, so then it gets even more interesting when we look at the numbers that come after those zeros,
Right,
starting with the 6th term.
right.
You know, it lists the number of possible labeled trees of diameter 5 for a given number of nodes, and they grow pretty fast. 1, 2, 7, 14, 32. It just keeps going up.
Yeah, and that increase in complexity, right? As we add more nodes, each additional node is like opening up more possibilities for connections and arrangements.
Oh, that's so cool.
Just a rapid expansion in the number of possible trees.
So it's not just counting, it's really capturing that combinatorial explosion.
Yeah, exactly. Like a window into the growth patterns of these mathematical objects.
Right, like we could see it happening.
Precisely, and that's just the start. The OEIS entry, it also provides formulas for calculating these numbers. It even links them to another sequence, A000065, which counts rooted labeled trees,
Wow, so it's all connected.
like building upon another.
Right. So we're not just looking at these isolated sequences,
Yeah.
but really like this web of relationships between all these different mathematical concepts.
That's one of the things that makes the OEIS so great, right? You
Yeah.
see these connections between seemingly very different areas of math.
Absolutely.
Like this one little sequence is a piece of a larger puzzle.
It is. It
Yeah.
is. Okay, so we've got this sequence, right? It's A000147. And it tells us, like, how many of these labeled trees of diameter 5 we can make with a certain number of nodes. But how do those formulas actually work? What's the link between, this sequence and the one for rooted labeled trees?
Yeah, well, the formulas, they're really cool because they use the idea that any tree of diameter 5, you can kind of break it down into 2 rooted trees of height 2. So they basically count all the ways to make those rooted trees and then stick them together.
Ah, so it's like breaking down a big problem into smaller pieces.
Exactly, yeah. We figure out the building blocks, and then we can count all the different structures we can build.
I like that. So the formula is like taking into account what all the ways to label the nodes within each of those little trees, and then like the ways to combine them.
Yeah, exactly. It's all about the arrangements.
Like a combinatorial puzzle.
Yeah, absolutely. And the connection to rooted labeled trees, that sequence A000065, that kind of gives us a foundation to build these calculations on.
Right. So we're seeing how different sequences in the OEIS are like connected.
Yeah. It's such a cool example of how, things that seem different, they're all related.
Absolutely. Now, we've been talking about, the structure of these trees kind of abstractly.
Right.
Are there any real-world applications for these labeled trees with diameter 5?
That's a good question. You know, while this specific type of tree might not have like direct everyday applications,
Yeah.
the underlying ideas, they're super important.
Okay, what kind of examples?
Well, think about the idea of trees in general.
Okay.
It's fundamental to computer science, especially for things like data structures and algorithms.
Right, like binary search tree.
Yeah, exactly.
Yeah.
Those are used all the time for searching and sorting data efficiently.
Right, right.
And then labeled graphs, those are used in network analysis, where each node is like an entity and the edges show the relationships between them.
So even though we're not out there, building physical trees with diameter 5, the math behind it has all sorts of practical uses.
Exactly. That's one of the amazing things about exploring the OEIS.
Yeah.
Sometimes a sequence that seems totally abstract, it can actually shed light on real-world problems.
I love that. Okay, so we've gone from this abstract world of labeled trees of diameter 5 to thinking about some connections to real-world applications. It really shows that math isn't just about numbers and formulas. It's about understanding the structure of everything around us.
Totally. The OEIS gives us this incredible tool for exploring that structure,
Mm.
uncovering patterns, making connections.
Like a mathematical treasure hunt.
Absolutely. Each sequence is a clue to something deeper.
I feel like we could keep talking about this sequence forever. There's so much here.
Yeah,
Yeah.
absolutely. Always more to dig into. Like, we haven't even talked about the code in the OEIS entry.
Oh, right.
It shows how to calculate the terms using Maple and Mathematica.
That's true. So for our listeners who are like more into the coding side of
Yeah.
things, that's a really cool way to like actually play with the sequence, see those formulas in action.
Yeah, it's a great resource for getting into the computational side of number theory, for sure.
Definitely. And for anyone who might be feeling a little lost in the technical stuff,
Yeah.
I think the best thing about the OEIS is that it's for everyone. Like you can just start browsing the entries, see what patterns jump out at you, and then kind of go deeper from there as you get curious.
Exactly. It's all about exploration no matter what your background is.
Yeah, totally. So as we wrap up this deep dive into labeled trees of diameter 5, OEIS entry A000147,
Right.
is there one key takeaway you'd want our listeners to remember?
I think it's the way all these mathematical ideas are connected.
Yeah.
We started with this one very specific sequence, but as we went along, we found links to rooted trees, to graph theory, even algorithms.
Right. It's not just like a bunch of random facts. It all fits together.
Exactly. Math is this amazing tapestry, all these interconnected concepts.
And the OEIS is like, I don't know, like a map to help us explore it.
Absolutely. It lets us see the beauty of how it all fits together.
I love that. So to all our listeners out there, keep exploring the OEIS.
Yeah, you never know what amazing connections you'll find.
Exactly. And until next time, happy exploring, everyone.